Welcome to the first instructional video for our marine biology class. In this video, I thought I would try to review some of the concepts that we talked about pertaining to marine ecology. Most of this material comes from Chapter 2, though this will not be the only instructional video about Chapter 2. Oops, looks like we went a little too far there. Let's go back. So the central ideas and themes from this chapter surrounding ecology are as follows. We know that organisms have to expend energy to live, and they're attempting to achieve a balance. That balance is called homeostasis. There are physical factors that dictate where organisms can live, and we've talked about some of these in class, including access to sunlight and energy, the temperature of the system, the salinity, exposure, something we haven't talked about much, drying out if you live on the shore, for instance, and the pressure. And we also know that species are not alone in the environment. They interact with one another, and those interactions can influence where organisms can live. Competition is a big thing. Continuing with the big ideas that we've started to discuss, we know that ecosystems are made up of many different things. They're both interacting communities of organisms and the physical environment. It's the combination of the abiotic, the physical pieces, and the biotic that combine to make a dynamic ecosystem. We haven't talked about this yet, but in Chapter 2, we note that organisms typically grow at really fast rates, an exponential rate. And they do that when materials and resources are abundant, but eventually those resources become limiting and they reach a carrying capacity. The environment caps the total population size and the growth rate levels off. That last point is important when we talk about algal blooms, for instance. And then we know that energy is the key. The more energy there is in an ecosystem, the more productive it is, and that energy is able to flow, and it flows from producers who capture solar energy, or perhaps chemosynthetic organisms, such as those that live in hydrothermal vents, through consumers on up a food web. So, lastly, we talked a little bit today about the 10% rule, both with respect to the size of organisms that or the size of prey that organisms can eat, and also how much energy is actually incorporated into bodies and devoted towards reproduction. In other words, how much energy can move up the food chain, and it's about 10%. And the last thing that we can say is that everything is recycled within ecosystems. Nutrients are moved around the oceans, except for energy. Once energy has been used up, it's gone forever. So to focus on some of the things that we really talked about today, we talked about the environment, and we focused on abiotic factors. Now, the habitat, of course, is the physical space in which an organism lives, and that habitat is defined not only by the climate, if you want to call it that, the abiotic factors, but also by other organisms and by the bathymetry, for instance, the topography, if you will, the rise and fall of the seafloor and its composition. So some things that are abiotic factors might be, are you living in an environment where you will experience the pounding surf and the movement of water? This environment also would potentially risk exposure from drying out when the tides move back. What kind of temperature do you experience? And as we talked about, do you live in the tropics, where the solar input is relatively constant throughout the year? Or do you live in a seasonal sea, where the amount of solar energy will change over the course of the year depending upon what season it is? Salinity may change. We think of salt water as being constant, but maybe you live in an environment like a tide pool where as the water evaporates, the water that's left behind only gets more and more salty, or an estuary. And then we talked about this kind of triple intersection of distance from land, the depth in the water column, and whether or not you have access to the seafloor as helping to define what the habitat looks like and what resources it has. So in this picture you can see the photic zone here as a relatively thin layer, 200 meters deep worth of water, where light penetrates and is rich enough to support photosynthetic life. And you can see a little bit of the different zones that we have within the sea. And there are more zones than this. But it underscores how important it is to be in shallow waters that are close to shore, nutrient rich, and bathed in sunlight. So to review, sediment type and how coarse that sediment might be, the pressure you experience based on depth, what the salinity profile is and whether or not that salinity changes over the course of the day or with a tidal cycle, exposure and wave action if you're at the shoreline, the temperature of the water and whether or not you may be exposed and dry out, and how much solar energy is placed into that ecosystem, along with nutrient input and whether or not you're in contact with the bottom. So all of those things are non-living factors that help to define the habitat. Now, as you imagine, organisms have preferred tolerances where they are operating at their optimal um, pace and metabolism. And as we move away from whatever that optimal range is, and this might be with respect to temperature, pressure, pH, salinity, things like that. As we move away from whatever that optimal value is, we'll see a decline in the abundance or size of the population. So organisms struggle out in the tail ends in a zone of stress, but do very, very well and are abundant in whatever that optimal range is. Now, of course, the environment may change, and animals can move, sometimes in response, and they are highly adapted, of course, to their environment. And animals are also, or organisms in general, are very good at maintaining an internal environment that is different from what their surroundings are like. So what kinds of environmental factors affect the distribution of organisms? Well, remember that they're always trying to stay in some kind of balance, stay within those optimal tolerance values. So as changes happen to the external environment, organisms have to make internal adjustments so in response and keep things steady and operating at that high clip. So that's really the task of homeostasis. And really, that's the 90% of the energy that organisms take in that is not devoted to more bodies and adding to biomass. So organisms have a couple methods or adaptations to stay within an optimal range. One will be simply if the environment changes to move to an environment that's more optimal. But not all organisms can do that. Some organisms are sessile and are stuck to the bottom or live within the sediments and can't move. So instead they have to change their internal body chemistry and work very hard, use a lot of energy to maintain the right osmotic balance and salt balance, for instance, um, and to withstand wide ranges of temperature change or the pounding surf and things like that. Okay. So biotic factors are very important too. So as organisms fight with one another for access to limiting resources. So competition between species, predation is the primary example, parasitism is another, and also competition within species affects individuals and affects populations. So if you take that abiotic piece, like let's say the sediment size and the particles for an organism who lives in the sand, and you take the type of food that they like and its availability, we can describe the niche. We can say that this blue box for species B describes the optimal range and intersection of what's the best sediment size and food size for that organism to be successful. And you'll notice here that in species A, it's a little different in terms of its optimal food size and its preference for sediment type, and the two interact, and that's shown here within this green. So whenever two species have overlapping niches, and you'll notice that they're not completely overlapping, they're just touching upon each other, competition will ensue. And typically, one species will win and another species will lose. and we'll experience something called competitive exclusion. And so let's imagine species B is a better organism as it battles for those limited resources and can outcompete species A. Well, the effective niche then is not the entire yellow box, but it's the yellow box with this notch taken out of it because competition has removed that portion of the habitat, um, that portion of the environment from species A. So we were talking a little bit about the 10% rule, so let's put that a little bit more into play. So here's a very simple food, um, not really a food web, but a food chain. So we have a primary producer, let's imagine it's a seaweed, and seaweeds are fed upon by urchins. Urchins are grazers. They are first order consumers, in this case an herbivore. But urchins can be preyed upon by helmet snails, and then those helmet snails might be eaten by a fish. So you can see we have the energy from the sun being stored in biomass in the seaweed, being transferred to the sea urchin, transferred to the helmet snail, and transferred to the fish. Now, in terms of the 10% rule, we know that there's an ecological efficiency or perhaps inefficiency that says 100 units of energy here, well, only 10 of those units end up as biomass in the next step up the chain. So for every 100 energy units incorporated into seaweed, there are 10 energy units in the sea urchin. There would be only 1 energy unit in the helmet snail, and there would be zero point 0.1 energy units distributed into the fish. And so that sets up what we call trophic pyramids. Each of these represent a trophic level, a level in the ecosystem at which organisms obtain nutrition. Are they primary producers or are they consumers? And where are they consumers? Are they primary consumers, first order consumers feeding directly on the seaweed, or are they somewhere higher up the chain? So as that energy is passed on, the amount of energy that can be built into bodies farther and farther up the food chain diminish. So what does that look like? We can look at that one more time, and it turns into a pyramid. So the biomass that's built into the primary producer level is 10 times bigger than the primary consumer level, than the secondary consumer level, or what we might call the tertiary consumer. So in class I was mentioning that tuna might sit way up here, maybe even one more level above. And so for that 500 calories worth of tuna, it took 10 times as much, 5,000 calories of a tertiary consumer, 10 times more. That would be not 5,000, but 50,000, and so on down the line. And so when you hold a can of tuna in your hand, what you're really holding is the end result of a funnel, a winnowing of energy from the primary producer level to secondary or primary consumers and on down the line. So that 10% rule is really important because it really tells us why large animals that feed high up on a food chain are very rare, both in the marine environment and in terrestrial environments. It's not just a marine issue. So that's basically a review of what we tried to talk about today in class. So let's talk about homework for Thursday. I don't see you guys on Wednesday, but in your F block double, I need you to come in having done the following. So we're talking a little bit about niche, which is the role of the organism or how it survives in the environment, what job it does and how it does it. So I'm asking you to look within your text and find 2 organisms, hopefully really different organisms, and I want you to describe the niche that each one of those organisms occupy. So how does that organism or each organism gain energy? What's their sources of nutrition? And what trophic level does it occupy? Where on the pecking order is it in terms of energy? Where would you find this organism? Where does it live? What zone in the ocean? Is it at all latitudes, for instance? And then, based on what you find, what abiotic factors does it face? If I live in the intertidal, that's very different than living on the abyssal plain, way down deep in the ocean. And then lastly, thinking about each of the organisms individually, can you describe some specific adaptations, at least 2, for each organism that permit that organism to be successful? Describe how it's adapted and built to do the job that it does. So that's our video for today. We will see you in class on Thursday, and hopefully you will have done this assignment.